Okay. Okay. Nice. Thank you, Huji. Thanks for the invitation. And hello, everyone. Hope you're having a nice day at Hawaii. Sorry, my flight got delayed, uh, so I could not make this presentation in person. But uh, hopefully, by the panel, I'll be in person. And if you have any questions that you want to ask in person, so I think after the panel, I'll be like also happy to interact. Okay, so let's get started. So I'll be presenting our work, uh, a series of work. So the working title is Keep It Simple While Building VLAs. So I'll talk about like different VLA designs and like some of the work we have done around building VLAs in this talk, and hopefully by the end of it, I can give you a good overview of how the VLA or vision language action landscape looks like and what are like the potential uh, potential design choices and what are like some good directions. Okay, so let's get started. Um, so we are all very well aware uh, of this really rapid progress and evolving state of robotics. Um, so so there are like a lot of companies, a lot of startups who are pursuing robotics. So here I've shown some of like the prominent VLA, some of the prominent robotics companies, and there are many more from Physical Intelligence, Toyota Research. They're actually, because they're able to do tasks uh, uh, much more easily as compared to what previous people would have been able to do, let's say a couple of years back. Um, and I would say a lot of this progress can be attributed to vision language action models. So what are vision language action models? Just like LLMs, which power language understanding, and VLMs, which power vision and language, VLAs kind of like extend this philosophy to also build upon them, and they extend it to also actions for, let's say, robots, autonomous cars, manipulators, etc. The generally, like typically the VLAs are built on top of existing pre-trained VLMs. So VLMs would be, let's say, pre-trained on large-scale internet data, and VLAs are generally built by like adapting them to also reason about actions. So, so if we think about it, the VLAs in the existing literature can be classified into three categories. So here I have listed them. So they are either, so I'll go over them in more detail later on, but like the general categories would be discrete token VLAs, generative head VLAs, or custom design VLAs. And I'll go over them one at a time. So let's start with discrete token VLA. So this is like the one of the simpler designs. So essentially, what this design does is that uh, in your existing language vocabulary, so your VLM would have like an existing vocabulary of language. What discrete token VLAs would do is like they would introduce some new tokens. So these would be specialized action tokens, um, and then and then you would, instead of predicting language, you would fine tune your VLM to predict now these new action tokens, essentially. So that's like would be like my 1 minute summary of what discrete token VLAs are. But as you can see with this design, there are like some limitations. One is that uh, you can only do few number of tokens, right? You could do, let's say, 10,000 tokens or 1,000 tokens, and that has like a limited action resolution. And I think the bigger problem, bigger issue, or bigger challenge here is that it compromises the existing language representation, because what you're doing is replacing or changing the vocabulary in some way. So it could like tend to confuse the existing VLM. And that's why we find that these such models would rapidly deteriorate in their language understanding capability. And one of the like very cool examples, or the early examples of discrete these kinds of VLAs would be Open VLA, um, which was published in Coral 2024. Another another interesting design is this design of generative head VLAs. So what I mean by generative head VLAs is that we start off with a VLM, and then we ask the VLM to predict some kind of latent vector, and that latent vector is then used by a separate head, and which is often referred to as an action head, which then uses that latent vector to do a generative modeling on the action. So that generative head would either be like a diffusion or flow matching head that takes in that is conditioned on this latent vector that is predicted by the VLM, and then it predicts an action. The the challenge with this design is that this action expert is actually not a pre-trained component. This is something that we introduce later on, and that reduces the generalization of such a design. The other thing also is that it also compromises the language representation, because the VLM, if you think about it, it's not actually meant to produce these latent vectors. It's actually meant to produce language, right? So when you backpropagate uh, your VLM to produce these latents, it tends to also compromise the language understanding of your VLM. The third design is kind of like a overarching category, which is like where instead of these, if your if your VLA is not falling into one of these categories, it may be into um, people go for like some very custom designed architecture. One of the examples would be Open VLA OFT, or like Pi Zero Fast, which involve like significant architectural changes on top of the VLM and require like specialized training pipelines. So I think like these three, if we think about it like from these three categories of VLA design, um, there is actually one more. So these are all of these are like monolithic designs because they are like directly predicting actions. One other way of like building VLAs would be, how about we don't go with this monolithic design, but divide the VLA problem into two components. First is keeping the VLM as it is intact, and then asking it to produce some kind of explicit representation, which I'll talk about later on. And then using a very specialized policy, which takes that explicit representation to predict actions. And the good thing here is that the specialized policy could be the best of, could be could be like suited for the particular task you care about. So it could actually be like a 3D policy, which I'll talk about more later on, but it could be like any specialized policy. So in this design, we try to combine the strength of the VLM as well as the strength of like your policy, because your VLM could be good at just generalization and predicting like uh, could be good at like generalization kind of task, and then your policy is kind of like specializing on that explicit representation, and then it could be suited based upon the task. So here the design is uh, motivated by being able to leverage the advantages of both these designs. So this we explore more in this work called Hamster, which is hierarchical action models for uh, open world manipulation, which appeared in iClear this year. So now I'll go like more into detail of Hamster. Um, so here is a quick video that kind of like explains what's happening. So like given any instruction, the first thing that happens is that the VLM predicts this. The VLM is asked to predict a set of points as well as uh, gripper values, and then based on these points, we can create an explicit trajectory of what the task should be. And we overlay this trajectory on top of a specialized policy, then then doesn't have to uh, do the open world generalization. It just has to predict the explicit actions. Let me play that again. Um, so for example, here the task is put M on Mona Lisa. Then the VLM is very good at the open world generalization, and it can, like, let's say, recognize where M is, where Mona Lisa is, and it can predict this explicit sequence of trajectory action. So it can predict this, okay, first I have to go to M, then I have to go somewhere on top of Mona Lisa. Now for the specialized policy, we can actually, it need not worry about M or Mona Lisa. It just has to know that, okay, I have to pick up this object and put it at the location specified by my VLM. So it can just focus on that action understanding part. Okay, and then it can also take in the 3D and everything, which the VLM is generally uh, not conditioned on. So that's like the design of Hamster. And in Hamster, uh, the critical part is, how do we build Hamster? Is that we if you see, the VLM is predicting this trajectory. Now the crucial part for us is to, like, create the right set of training data to fine tune our VLM so that it can predict these kinds of trajectories directly. So we fine tune Hamster. We fine tune the VLM part of Hamster on a variety of data sources, uh, which cover a lot of different kind of tasks and stuff. So for example, one thing we fine tune our VLM is this on pixel point prediction task. So essentially, these would have tasks like find all instances. For example, here it would have tasks like find all instances of the cushion. So then it becomes very good at, like, pointing at things. The other thing could be locate the object between the marked items, right? So essentially, what the VLM is getting is learning is, how do I point at things with these pixel point prediction tasks. And we use, like, existing data sets like Elvis and RoboPoint, which have a lot of these point um, labels with point prediction. The second thing that we use is that as you might know, that, like, when you fine tune a VLM, we don't want it to lose its language understanding capability. So we keep in some existing large scale existing VQA data that has a lot of the semantic reasoning capabilities, that has a lot of the semantic reasoning questions, right? Um, so that the VLM doesn't lose that capability. Next, we also fine tune this VLM with a lot of with a larger scale simulated robot data, where the task is very similar to the task I showed you before. For example, screw the green light bulb um, on the handle. So here we use simulation to generate a lot of these trajectories for the VLM, where it's kind of like a combination of this point prediction task as well as this trajectory building task. And the last part is, like, in simulation, we can have much larger data set, but like we don't have that large data sets in real that are open source. So we also fine tune on a relatively small amount of open source open source real robot data sets which have these kind of like tasks, right? So now so if you see, there is like a variety of tasks that we fine tune our VLM on, um, and and that leads it to learn this zero shot trajectory um, building property in the VLM. Here, I'm showing like a very cool example. So here, given this task of put the put the M&M on the cup, you can see that the VLM predictions are actually pretty robust to camera changes, which is which we directly get from, because we are fine tuning VLM. We get this kind of robustness, which is very hard to get if you're just fine tuning, if you're just using robotics data, right? So here the power of the generalization capability of the VLM really shines. What's even more surprising, and I think what actually demonstrates the power of hamster or this hierarchical design is, let's say we had these tasks like put the cup in the cup holder, or put the screw the bulb. So these tasks are only present in simulation. Um, so we have only simulation data for these tasks. We don't have any real world data for these tasks. But uh, why? But the VLM has this. When we are fine tuning the VLM, it has this ability to transfer knowledge across domains. So even if when we train in just in sim, this can zero shot transfer to real. Uh, it's a way to do sim to real transfer, because this task is now at a higher level, right? And we see that the VLM can transfer to real world examples. So here, uh, which is like very hard to do if you're just doing like sim to real transfer in robotics. But this high level explicit prediction task does transfer in the real world, as you can see here. And what's even more surprising is that it comes in with all the good things about VLMs, is that it can also transfer to very out of domain things like sketches here. So here we just drew like, okay, a sketch with something that looks like a cup, something that looks like the holder, and the VLM would actually transfer and give you very reasonable prediction even in this very out of domain scenario, which is very surprising, um, and shows how the VLMs how this pipeline can be a good way to do uh, sim to real and combine like multiple domain source of data. In terms of results, uh, so if you remember, the design had two components. First was like the VLM component, and then a 3D policy on top of it. What we found that in real world, this design of like hamster is better than either like these monolithic policies like OpenVLA, and it's also better than just fine tuning your 3D policy like RBT2 or 3DDA. But if we use like this hierarchical design, we get better results than both the monolithic VLAs, as well as 3D policy. So this design is actually combining the best of both here. So before I move forward, it would be good to highlight like some of the failure cases of this design. So the kind of failures that we see are like sometimes the VLM is not perfect. It will still predict some errors. For example, here, pick up the Pookie and put it on the pan. It's not picking up the Pookie correctly. It's not reading it properly. Other kind of and hence it goes for the wrong object. Other kind of design would be since the only information that is being transferred from the VLM to your 3D policy is this trajectory. It may not actually, so sometimes the 3D policy uh, might not follow the trajectory. So there sometimes we see those kinds of failures. For example, here the VLM is predicting the right thing, but if you see that the policy actually goes and um, puts the object on the incorrect bowl. Um, and then the third kind of failure is like even if the VLM predicts the correct thing, and even if the 3D the policy is following the trajectory, sometimes the actions just fail. So these are like action failures. And we see that a lot of the failures actually are depending on different design are uh, are either due to failure, or so we see like a mix of these kinds of failures here for such a policy. And it would be good the same time as we published this work, there was like a lot of like community effort and many concurrent works that I want to highlight, including like high robot from Physical Intelligence, Groot from NVIDIA, and Helix from Figure Robotics, uh, which are now using this hierarchical design. Um, and it's become like a very common design now in the VLA architecture space, with different teams having their own flavor to this hierarchical design. Um, Now, if you remember that this is like a schematic representation of the hierarchical design, and here uh, there are two components, the VLM and the 3D policy. I'd like to like focus a bit more on the 3D policy because they are actually so these are like policies which take in like scene depth and like more information like camera calibration, but they are like pretty efficient. So like if you have like a specialized task, this could be like really good if you have like the right sensors and stuff. So I'd like to give you like a brief uh, a brief peek into like some of these policies, and specifically our work called RVT, which is robotic view transformer for object manipulation, that I'll like quickly go over here. So what is RVT? So RVT is this 3D policy. So essentially it takes in 3D and a language instruction and predicts it's a multitask policy. The cool thing about this such policy is that it's very efficient. So with just like very few demos per task, so like in the order of 10 demos per task, it could give you uh, a decent enough success rate, which is like very hard to achieve with just like 2D policies. So what's happening in RBT? So like a very quick overview. So let's say we start off with an instruction and a scene. What RBT, so your scene will have, let's say, input RGBD images. We have, let's say, depth and also the camera parameters for each of these cameras. The first thing we do is like we create this consistent 3D, like explicit 3D representation point cloud by using all the camera and depth information available in a scene. Then we re-render our scene using like this fixed set of views. So instead of using the originally provided views, we use this set of canonical views, which we call virtual views, which are essentially right at the top or left, right. So we can see that even if the input views change, or if the input views are moving, these canonical views are like always fixed. And that we found to like really assist in assistant learning, and I'll show you how. Um, Given these canonical views, we then learn a transformer that looks across the views and predicts these 2D heat maps. Essentially, um, these 2D heat maps uh, are like location of where the end effector should go next. One thing to note is that this is like inherently multimodal. So for example, here the task was stack the teal blocks, and the top view you can see there are multiple teal blocks. So the uh, the heat map is predicting the location of these multiple teal blocks. And what we do is then we do the inverse operation of, like, instead of rendering, now we take these 2D heat maps to predict like a 3D heat map, which is essentially for each 3D point we find out the location of the 2D point in all these heat maps to get like a 3D point, 3D value of that heat map. And you can see here is the predicted 3D heat map. So you can see the heat map is on the teal points, and it's like also multimodal. And then we use these heat maps to find the highest score point as the gripper location, uh, and corresponding features from the heat map to predict like gripper, other information like the gripper rotation and state. This is then fed to the controller, which then moves the robot to that next state, and this pipeline keeps on proceeding here. So here I'm essentially just showing how at each time step of prediction we have an update, and the policies predicting these different sets of heat maps, and completing the task. So that was RBT. We built upon RBT to like make it faster and more precise. So here, uh, so we refer to as RBT2 is essentially we extend RBT to take this a multi-scale design approach, where instead of just doing this prediction at one scale, we do it at two scales, so that we could do like very precise predictions. And this allows us to actually do some pretty complicated tasks with very few demonstrations. For example, here, like plugging in the plug in the socket, or like these insertion tasks, which are like which have like very little tolerance, but with very few demonstrations and extending this multi-scale design, we are able to do it. Uh, and it would be like very hard to replicate to do some of these tasks without this explicit 3D representation, and like really leveraging this multi-scale design. Okay, so now let's come back. So I spent some time over explaining the 3D policies, but then let's come back to our family of VLAs, right? So we had our like three families of VLAs, existing family of VLAs, like discrete token design, generative head, custom design, and then we introduced this hierarchical VLA design. But so we thought, what about a design that's even more simpler? Um, like, do we? So we thought hard. Like, do we actually need some of these components, like these action tokenizer, or like these generative heads, or like a custom design? How about the simplest design, which is you take a VLM and then ask it to predict actions as just text. So the actions, so there's no change uh, either to the VLM, or like any new component. And we refer to it as like VLA 0. And so so this is, we call it the no modification VLA. And let's look at our very recent work called VLA 0, building state-of-the-art VLAs with zero modification, which dives deep into this design and like explores it explore different parts of it. Okay, so what is VLA 0? So as I said, this is like a no modification VLA design. So there's no modification to the VLM. You essentially predict action as text. So there is no change in tokenization because text is what the VLMs can already predict, right? There is no new architectural component, and it's mostly the key is in just training the VLM uh, correctly. So that's like the trick in training recipe, right? So that's VLA 0. Uh, and we would think that, okay, this is like such a simple design. Does it actually work? Like, how does it compare to other designs that where we had to like explicitly build tokenization and stuff like that? So one of the most popular benchmarks where people can uh, reproducibly compare the results is called Libero. Uh, uh, what we found, which was like very surprising to us, that this simplest design actually outperforms all uh, all of the other architectural options when there is no large scale pre-training. So like this is like a fair comparison. None of these models have been pre-trained on any large scale data. They're just fine-tuned on this. The architecture is just fine-tuned on this um, particular set of tasks. And then out of all designs like Pi, Fast, Small VLA, Open VLA, OFT, uh, Pi Pi 0.5, this design actually performs the best. What's even more surprising is that even in the mix of these things, we also add models which have like a lot of large scale pre-training, right? Like Pi 0, Pi 0.5, uh, knowledge installation, GRUT N1, Molmoac, like all these popular models. And we have VLA 0, which is not fine-tuned, which is not pre-trained on any large-scale action data and just like simply fine-tuned on this data set. It's actually better than most of them. So which was like very surprising to us that this very simple design, which doesn't require uh, which is essentially like a V0 baseline, is better than any other design or model which has been like fine-tuned on lots of action data and stuff. Um, so now let me go a bit more. Uh, let's dive a bit more deep into what's actually in the architecture. So it's pretty simple. So like in any LLM, VLM, we have a system prompt, and here in our system prompt is essentially just defining the task for the VLM, saying that, okay, analyze the image, and you have to predict the actions as this sequence of integers, uh, space center, space separated sequence of integers, right? So it defines the task for the VLM. The VLMs are can take in, they are very flexible. They can take in multiple options. They generally can do charting. So like it's very easy for us to provide it like multiple images. So here in real, we'll provide it, let's say left and right image. And then we have the and also the user prompt, and then the VLM just predicts like output actions as text, which we uh, which we take it as it is and then just normalize it into like the floating point values. Uh, and and that's it. So that's like the entire VLA architecture. Um, this not only in sim, this like also works in uh, TVL in real. Especially we compare to small VLA on this like SO100 platform. It's a very nice platform, easy to like play around. And this small VLA is one of the popular VLAs on this platform, released by Hugging Face, which is pre-trained on like a lot of SO100 specific data. But like we find this like simple design with no pre-training and just like fine tuning on like small demonstration is actually better in real as well. Um, sorry, I won't go into like lot more details here. in interest of time, but please feel free to like check out this work. We just open sourced it. We just like released the paper last week, and trying to will open source the code soon. Great. So I think that's like that covers most of the technical bits I wanted to cover. So in summary, I've shown you like some of these give you like a good sense of like the design space of VLAs, and like what are like these different categories of VLAs. And if I three key messages that I want you to take home with is that there are these other designs called hierarchical VLAs, which are very good at combining the strengths of VLMs and, let's say, your specialized policies here, 3D policies. Then if you have the sensors, and if you want to make like very task specific precise models, 3D policies are a great option. And these are like very efficient task specific learners. I'm sure Katrina would also talk about them a bit more. So those are policies, something you should consider as well. And the third thing that I talked about is this monolithic the simplest monolithic design VLAs that takes in just 2D images like any other VLA. And it's like we find that this simplest design is surprisingly very effective, um, um, much more much more effective than other designs, even when it is like non-pre-trained. Um, so that's it. I think that covers everything I wanted to cover, and we are almost at time, so I'll be very happy to take any questions. Thank you.